This section introduces what happens to matter at the nanoscale, the window from 1 to 100 nanometers. Shrink a chunk of matter until a large fraction of its atoms sit on the surface inside the 1 to 100 nanometer window, and the substance stops behaving like itself. Melting point, color, conductivity, reactivity, properties you treated as fixed constants of gold or silicon become functions of size. 2 levers drive it. The first is the surface-to-volume ratio, exploding as volume falls faster than area. The second is electrons squeezed into a box, small enough that confinement quantizes their energies. The chapter's thesis is this inversion. At the nanoscale, geometry becomes chemistry, so a nanomaterial is defined not by what it is made of, but by how small it is made. This L1 concept explains how shrinking a solid puts a single number in charge of everything. Shrink a solid and one number governs it all, the fraction of atoms sitting on a surface or an interface, rather than buried in the bulk. That fraction grows as roughly 1 over d, reaching near half the atoms at 5 nanometers and only 3% at 100 nanometers. That single ratio regenerates the whole chapter. The melting point drops, the color shifts, an insulator or a catalyst appears, each one as a consequence of the surface fraction. The taxonomy of 0D, 1D, 2D, and 3D merely counts the directions squeezed below the electron's Bohr radius, discretizing its once continuous energy spectrum. The telos of the chapter is that size is itself a material property. Bulk is the limit where surface vanishes and the number stops mattering, which is exactly why the effects switch off above about 100 nanometers. This section explains what small size does to a material's surface. Cut a solid into pieces and you conserve its volume, but multiply its surface. That asymmetry is the whole chapter. Hold mass fixed. Shrink the edge length by a factor of 10, and the number of cubes rises by 1,000, while total surface grows tenfold. The invariant the rest depends on is that the surface-to-volume ratio scales as 1 over L. The author's arithmetic anchor makes the scale visceral. Take 1 cube of side 1 meter, carve it into 1 nanometer cubes, and you get 10 to the 27th power pieces whose collective surface reaches 6,000 square kilometers. The author calls this the power of nanosize. Everything downstream in the book, the optical, catalytic, and mechanical divergence from bulk, is a consequence hung on this one geometric fact. At the nanoscale, a material is almost entirely its own surface. This section explains the single scaling law that makes nanomaterials behave unlike bulk matter. Cut a fixed lump of matter into ever finer pieces, and its total surface swells without bound. The whole engine of the chapter is this: surface scales as length squared, volume as length cubed, so their ratio runs as 1 over the edge length cubed, so their ratio runs as 1 over the edge length. Hold the mass constant and shrink the edge, and the surface-to-volume ratio diverges. The fraction of atoms sitting on the surface climbs toward 1. That single scaling law is why nanomaterials refuse their bulk properties. Every optical, thermal, and catalytic anomaly downstream is this one ratio cashed out. The chapter earns it twice, on cubes and then on spheres, from nothing but mass balance. The geometry differs, but the exponent gap does not. Predict the next shape yourself, and the 1 over the edge length survives it. This section explains why particle size takes over the properties of a nanomaterial once a crystal gets small enough. Shrink a crystal and one number takes over, the fraction of atoms sitting on a surface which grows roughly as 1 over the diameter. Below about 10 nanometers, that fraction stops being negligible, so every property carrying a surface energy term begins to drift. Melting point falls first because surface atoms reach liquid, like mobility at lower activation energy. The same logic then propagates to mechanical, electrical, magnetic, optical, and catalytic behavior. The chapter's real primitive is this. At the nanoscale, size stops being an intensive parameter and becomes a tuning knob. You can predict any subsection by asking which surface term dominates. The sign can even flip. A nanoparticle locked inside a matrix superheats because the matrix's confining pressure now sets the energetics, taking over from the free surface. This section explains why a material's basic constants are secretly a function of its size. What a bulk textbook calls a material constant, melting point, conductivity, band gap, this chapter reveals as a disguised function of one variable, size. Shrink a crystal below about 100 nanometers and the fraction of atoms sitting on the surface, undercoordinated and high in energy, stops being negligible. Below about 10 nanometers, it dominates. Since that surface fraction scales as roughly 1 over d, where d is the diameter, every property the surface atom's weight slides predictably as the diameter falls. That includes the thermal, mechanical, electrical, magnetic, optical, and catalytic properties. Gold's melting point drops by over 300 degrees Celsius. Here is the primitive to carry forward. At the nanoscale, geometry becomes a tuning knob. You no longer choose a material. You dial d, the diameter, and let the surface rewrite the constants. This section draws the single lesson that runs through the whole chapter. Function comes from geometry rather than chemistry. That is the thesis, and it arrives through creatures that share their materials but not their behaviors. Lotus wax, butterfly cuticle, peacock keratin are unremarkable substances. The structure, at around 100 nanometers, does the work. Morpho's blue and the peacock's eye carry no blue pigment at all. The color falls out of light, interfering across periodically spaced ridges, with the spacing set to the wavelength. The lotus non-wetting is roughness at scale, not a Schlecker-Malik. Nature builds these by bottom-up self-assembly, growing the pattern. Human fabrication carves top-down. That is why the biological versions are tougher. The generative move is this: to get a property, pattern, ordinary matter at the scale of the interaction you want, and the function emerges for free. This section explains why structural color and structural function are one pattern. Before any lab, nature already ran the search, and its answer is always the same: put ordinary matter into a periodic structure at the wavelength or contact scale, and function appears without new chemistry. Consider 3 cases. The lotus, with papillae around 120 nanometers, yields superhydrophobicity. The morpho butterfly, with submicron ridges, yields blue by interference. The peacock, with a melanin lattice, tunes color by spacing alone. The pigment is incidental. The geometry is the mechanism. So the chapter stands in the book as an existence proof. Bottom-up self-assembly already outperforms top-down fabrication, and biomimicry is merely reading the structure off the organism. Here is what updates you. Color, adhesion, and dryness are not materials, but lattices. Change the spacing, change the property. This section explains how every method of making nanomaterials falls onto a single axis. Every route to the nanoscale is one of two directions: subtract from bulk or accrete from atoms. Top-down carves. It mills, etches, and uses lithography, reducing existing matter by force. Bottom-up grows. It nucleates particles, then assembles them chemically or biologically. The asymmetry that organizes the whole chapter is that direction predicts quality. Force leaves scars. Top-down inherits surface damage, internal stress, and defects that bleed electrical conductivity. Accretion moves toward thermodynamic equilibrium, yielding cleaner order and more homogeneous composition. So the two directions are not neutral mirror images. One fights entropy and pays for it in defects. The other rides it. Everything downstream, every named technique, sorts under this single binary. This part explains the single axis underneath every fabrication method in the chapter. Every method is one of two directions along that axis. One direction carves the nanoscale out of bulk, the top-down move. The other accretes it, atom by atom, cluster by cluster, the bottom-up move. The generative primitive is this: the direction of approach fixes the material's distance from thermodynamic equilibrium. Subtracting injects strain, dislocations, surface defects, and contamination, a body forced far from equilibrium. Adding settles near it, with homogeneous composition, long-range order, and fewer defects. Bull, milling, and colloidal growth are the two poles. Lithography is the hybrid, a film grown up, then etched down. So the choice is never really about the tool. It is about which side of equilibrium you are willing to pay for. This section explains why a carbon nanotube's every property traces back to one geometric choice. Roll a single graphene sheet into a seamless cylinder, and every headline property follows from how you rolled it. The wrapping angle of the hexagons alone decides metallic versus semiconducting. The wall count and the diameter set the stiffness and the surface to volume ratio. That one geometric degree of freedom is the whole chapter's spine. Synthesis, structure, properties, and applications form a single causal chain rather than four separate topics. Every synthesis route is the same move underneath. Arc discharge, laser ablation, CVD, and HIPCO all vaporize or decompose carbon, then let it recondense on a metal catalyst. The method matters only because it fixes defect density and chirality control, which is to say it fixes where on the property spectrum you land. This section explains how the way a graphene sheet is rolled decides whether the resulting nanotube behaves as a metal or a semiconductor. Roll one graphene sheet into a seamless tube. The direction you roll it, a single pair of integers, n and m, fixing what is called the chiral vector, decides whether the tube conducts like a metal or opens a semiconducting gap. The rule is exact. The tube is metallic precisely when 2n plus m is divisible by 3. Otherwise, it is semiconducting. So 1/3 of the possibilities are metallic and 2/3 are not. That is the chapter's whole compression. A purely geometric choice, made at synthesis, propagates deterministically into the electronics, and from there into every application. Transistors, storage, reinforcement. Synthesis fixes structure, structure fixes property, property fixes use. The book's recurring thesis is that size and arrangement, not composition, govern behavior. Here, it reaches its cleanest instance. Same carbon, same bonds, different winding, different physics. This section lays out the single primitive behind the whole chapter on nanowires. Take a crystal and confine 2 of its 3 dimensions down to where electrons can no longer spread. 10 to 100 nanometers, while letting the third dimension run for microns. What remains is a single conduction channel, one free axis riding on a body that is almost all surface. That geometric move is the generative primitive for everything that follows. Every synthesis method, the chapter surveys, the VLSC droplet, the pore templates, is one trick for forcing growth along that surviving axis. Every property it lists, the depressed melting point, the diameter tuned color, the enhanced magnetic coercivity, is the same surface. Fix the dimensionality, and the bulk renegotiates itself. Predict the next property from the surface to volume ratio alone. This section explains what a nanowire really is and why its shape comes from confinement rather than chemistry. A nanowire is a material forbidden to grow in every direction but one. Every root in this chapter, the vapor liquid solid droplet, the anodized alumina pore, is the same move. Drive a species past supersaturation at a site whose geometry permits precipitation on a single axis. The one-dimensionality is a boundary condition imposed by the collecting site. It is not a property of the substance itself. Hence the chapter's quiet correction. The gold catalyst catalyzes nothing. Its activation energy matches seedless growth. It is a soft template, a shape selector wearing a chemist's name. Confinement makes the wire. Chemistry does not. A soft template, a shape selector wearing a chemist's name. Confinement makes the wire, and the chemistry does not. This section opens the carbon materials arc, and it explains why graphene sits at the head of it. Take one sheet of sp2 carbon arranged in a honeycomb. Every other carbon nanoform is a derivative of that sheet. Stack the sheets and you have graphite. Roll one and you have a nanotube. Graphene is the generative parent, the two-dimensional primitive from which the three-dimensional cases are read off. Its superlatives all follow from a single fact. Carrier mobility near 2.5 times 10 to the fifth power, square centimeters per volt. Second, zero effective mass, a modulus around 1 terapascal, 2,630 square meters per gram. These are one consequence of one thing. With only a single atom of thickness, there is no bulk. Everything is surface and the electrons move as if made. Synthesis then splits cleanly. You peel down from graphite or you grow up from carbon. Graphite or grow up from carbon. This section explains why graphene's extremes all follow from a single structural fact. Strip carbon down to a single sp2 sheet, and every superlative follows from one fact. The pi electrons that lay buried between graphite's layers are now fully exposed. Graphite is these sheets stacked. A nanotube is one sheet rolled. Graphene is the generative parent of both. So the record carrier mobility, the stiffness of about 1 terapascal, the transparency greater than 97%, and the surface area of 2,630 square meters per gram are all one thing wearing four faces, which is why the chapter's true axis is a single knob, defect and oxygen content. Every synthesis root and every property number is that one knob turned. At one end sits pristine mechanical cleavage, at the other sits cheap scalable oxidize, then reduce. Quality is traded against yield, and the whole field lives on that one trade-off. This part explains why permanent magnetism is decided by particle size. Permanent magnetism is a competition settled by size rather than a fixed fact of the material. A ferromagnet's remanence rests on domain walls that hold aligned regions in place. Shrink the grain past single, domain size, and the wall stops paying for itself. Coercivity first peaks, then collapses, because the barrier pinning the moment's direction, K times V, scales with volume, and once V is scales with volume, and once V is small enough, the thermal energy kBt flips the moment freely. The particle turns superparamagnetic. It is magnetic under an applied field and inert the instant that field is removed. That is the chapter's whole move. Geometry displaces chemistry as the control knob, and a magnet you can switch on and off is exactly what biomedicine wants for MRI, drug targeting, and hyperthermia. Netic under an applied field and inert the instant the field is removed. That is the chapter's whole move. Geometry displaces chemistry as the control knob, and a magnet you can switch on and off is exactly what biomedicine wants for MRI, for drug targeting, and for hyperthermia. This section explains why a magnet forgets its orientation once you make it small enough. Shrink a magnet and its memory starts competing with heat. A ferromagnet stores its orientation behind an energy barrier called kV, anisotropy times volume. That barrier is what makes hysteresis and what makes a permanent magnet permanent, because the barrier scales with volume. Shrinking the particle shrinks the memory. Past a critical size, the thermal energy kBt overtops kV and flips the moment freely. Coercivity is therefore non-monotonic in size. It rises as multi-domain grains shed their easy-to-move block walls, peaks at the single domain size, then collapses to zero. That collapse is superparamagnetism, magnetic only while the field is on, forgetting the instant it leaves. That is exactly why it is the biomedically useful regime. This section explains why nanoscale fillers earn their own chapter in polymer composites, and what that leverage costs. A polymer gains a filler's stiffness, barrier, or flame resistance in proportion to how much interface the filler presents. The driver is interface, not the mass added. Interface per unit volume scales inversely with particle size, so shrinking one dimension below about 100 nanometers lets 1 to 5% by volume do what 15 to 40% by volume of micron filler did. The dual of that leverage is its cost. The same surface hunger that buys the property makes particles clump, and a clump seeds cracks instead of reinforcing. So every processing route, in situ solution, is the tax. Agglomeration is the tax. In surface modification, whether organoclay or compatibilizer, is the price of keeping the interface open. Interface is the lever. Agglomeration is the tax. Clay or biocompatibilizer is the... This section explains why, once you shrink the filler, the interface becomes the material. A polymer's weaknesses, its brittleness, its flammability, its gas permeability are governed by how much polymer touches filler surface, not by how much filler you add. At nanoscale, that contact area diverges. So 1 to 5 volume percent area diverges. So 1 to 5 volume percent of micron filler cannot. The chapter's engineering tension follows from this. The gain is latent in that surface, and the surface exists only once stacked clay. Platelets are pried fully apart. That full separation is exfoliation. Merely sliding polymer between the platelets, intercalation, does not release it. Dispersion is the real problem. Let the particles agglomerate and you revert to an ordinary microcomposite. Everything after this, clay, nanotubes, boron nitride, barium titanate, is one pattern seen through different fillers. G. After this, clay, nanotubes, boron nitride, barium titanate, is one pattern seen through different fillers. This section explains why polymeric nanofibers are made the way they are, and the single primitive that the chapter turns on. Thinner fiber is stronger fiber. Less volume means fewer defects to nucleate failure, and the draw aligns the chains. So the whole game is diameter reduction. Mechanical spinning bottoms out near 2 micrometers because you are pulling on the filament with a physical force that cannot grip anything finer. Electrospinning changes the substrate of the drawing force. An electrostatic field, not a mechanical grip, does the stretching. Charge repulsion on the jet's own surface pulls it thin down 2 orders of magnitude to tens of nanometers. That is the primitive the chapter turns on. When a process is capped by how the force is applied, swap the force's medium rather than refine the mechanism. This section explains why fiber makers chase thinness and how electrospinning breaks past the limit that pulling alone can reach. Fiber strength climbs as diameter falls because the molecules line up tighter and carry fewer defects. So the whole gain is thinness. Mechanical spinning draws filaments by pulling, and that actuator floors out near 2 micrometers. Electrospinning swaps the actuator. Charge the polymer solution inside a strong field, and the induced charges repel each other hard enough to overcome surface tension, drawing a jet that whips into fibers tens of nanometers across, 2 orders of magnitude below the mechanical floor. Here is the primitive. When a mechanical draw hits its limit, replace the force with a field the material carries internally, and the limit moves with it. Everything downstream, the vast surface area, the roughly 90% porosity, the whole application list, is just a consequence of the diameter the field buys. It's it. The force is no longer external and fixed. It lives in the material and scales with it. Everything downstream follows from this. The vast surface area, the roughly 90% porosity, the whole application list, all of it is just a consequence of the diameter that the field buys you. This section explains why characterizing nanomaterials means inferring size rather than measuring it, and the single dichotomy that organizes every technique in the chapter. You cannot lay a ruler against something smaller than the light you would see it with, so inference replaces measurement. The chapter's spine is a single dichotomy. Either you strike the object with a probe whose scale matches the feature, Ångström X-rays against atomic planes, electrons against nanometer grains, and image it directly with SEM or TEM. Or you read a signal that couples lawfully to size and invert the law indirectly, the way XRD peaks broaden as crystallites shrink, light scatters, and absorption edges shrink, light scatters, and absorption edgesena. The move that carries the chapter is this. At the nanoscale, the observable is always a proxy, a broadening, a scatter, a shift. Characterization is the craft of running that proxy backwards. This part explains why you can never measure a nanoparticle directly and what you do instead. A nanoparticle is smaller than the light you would look at it with, so you never measure it. Instead, you measure a proxy signal whose distortion is a known function of the hidden dimension, and you invert. That split is the whole chapter. Direct methods, SEM, TEM, and SPM magnify past the eye and read the size off an image. Indirect methods, XRD, and the spectroscopies never see the particle at all. They exploit a law that ties behavior to scale. The canonical inversion is this. A finite crystal has too few lattice planes to fully cancel off. Bragg intensity, so its diffraction peak broadens inversely with crystallite size. Characterization is measurement by inference. Every technique trades what it resolves against what it must assume in order to invert. This section explains how shrinking a metal's grains changes the way it corrodes. When you shrink a metal's grains down to the nanoscale, the volume taken up by grain boundaries swells toward half of the whole material, and that single lever pushes corrosion in two opposite directions at the same time. More boundary means more free volume defects, the sites where localized attack nucleates, so dissolution speeds up. But that same extra boundary also gives passivating, alloying elements fast diffusion paths to the surface, building a more uniform and more protective oxide. Which of these two arms wins is not fixed by the metal, it is fixed by the medium, by whether the environment lets that oxide passivate. Here is the chapter's primitive. Nanostructuring raises the gain on a mechanism that the electrolyte selects, rather than improving corrosion resistance on its own. That is why you see both the record-thin graphene coatings and the anomalous cases that corrode faster than the bulk metal. This section explains what happens to corrosion when grain size shrinks to the nanometer scale. Shrink grain size to nanometers, and the grain boundary volume swells toward half the material. This is the same structural inflation that earlier chapters used to explain every size-dependent property, now turned on electrochemical decay. The surprise is that its sign is undetermined property. That intercrystalline fraction is, at the same time, where localized corrosion nucleates, the defects, the microvoids, the weak sites. And it is also the fast diffusion path that floods the surface with passivating species, building a more uniform protective film. Neither outcome wins by default. So, corrosion is the chapter where the book's master knob, properties scales with surface to volume, stops being monotone. Nanograined nickel passivates better. Neodymium iron-boron magnets corrode worse. One knob, opposite outcomes. This section explains how the whole catalog of nanomaterial applications collapses to one move. Every entry is the same substitution. Take a bulk technology throttled by one material property, then replace the material with a nanostructure whose size itself drives that property past the bulk ceiling. 3 examples show the single move from different angles. Nanofluids lift thermal conductivity through sheer surface area. Solar cells tune the band gap through quantum confinement. Antibacterial coatings trade on reactivity that only a vast surface to volume ratio grants. The chapter reads as a dozen unrelated devices. It is one function applied 12 times. The size effect thesis from chapter 3, finally cashed out as engineering. So do not hold the list as facts. Hold the generator. Name any bulk bottleneck, ask which nanoscale property relieves it, and the application falls out on its own. This section explains why every application in this chapter is one idea, wearing different clothes. Each is the same sentence with a single word swapped. A property that exists only because surface dominates volume at the nanoscale becomes the function of a device. Look at the catalog. Nanofluids monetize surface, amplified thermoconductivity. Ferrofluids monetize superparamagnetism. Antibacterial coatings monetize reactivity. The breadth of the list conceals that there is one generator, not a dozen. This is where the book's earlier claim, that size dictates property, finally cashes out as size dictates use. And the same surface that enables also extracts attacks. It drives agglomeration, so every application ships with a stabilization scheme. Predict the next entry by naming which nanoscale property it sells and what it must pay to keep that property stable. This section explains why the very property that makes nanomaterials useful is also what makes them dangerous. Every prior chapter sold one lever, shrink below 100 nanometers, and the surface area to volume ratio explodes, buying you strength, catalysis, and organs. This chapter reads the same lever backward. That swollen reactive surface is exactly what makes nanoparticles toxic, and their smallness lets them translocate past the body's barriers. The skin, the gut, the alveolar barriers, the skin, the gut, the alveolar wall, into blood, brain, and organs. Toxicity is the same function property with its sign flipped. The reactivity you engineered for is the reactivity that harms tissue. So the dose that matters is surface area rather than mass, and the same variables that tune performance, size, charge, and solubility are the variables that tune hazard. Bind a nanoparticle into a matrix and both collapse together. The risk was never elsewhere. Elapse together. The risk was never somewhere else. This closing section evaluates the cost side of the very property the book has been celebrating. The same knob turned for its cost turns the harm. 14 chapters celebrated that, below 100 nanometers, the surface area to volume ratio explodes and new properties emerge. This closing chapter evaluates that identical function for its cost. Toxicity is the size dependence. Chapter 3 pointed at biology, the same parameter turned toward the cell rather than a fresh property added on top. A smaller particle diffuses past barriers, the larger one cannot. The high surface area that made catalysis vivid now reacts vividly with cells. Utility and liability share one parameter, size. Read the arc's inversion this way. Every property that earned a chapter of praise reappears here as an entry route into lung, blood, and brain.